So there was this moment recently that sent a legitimate shockwave through the tech industry. For, over a decade, the story of serious AI compute was just painfully simple.
Oh, absolutely.
If you wanted cutting-edge performance, you bought NVIDIA H100s, you paid what everyone called the green tax, and then you just waited.
And you waited and waited in a line that was measured in quarters, sometimes years. It was just the price of admission.
That was it. The only game in town for the AI gold rush.
And that monolithic narrative is, well, it's finally cracking. The news that Meta, one of the single largest buyers of AI hardware on the planet, is exploring Google's TPUs.
They're tensor processing units.
Yeah. That is not just some engineering footnote. This is a strategic fork in the road for the entire future of semiconductors.
Okay, let's unpack that. Because for so long, we've been living in, the age of the TPU, the graphics processing unit. What we're seeing now feels like a high-stakes battle.
It is. It's a battle between the flexibility of that GPU and what the sources are calling the ruthless efficiency of the TPU.
Ruthless efficiency. I like that.
It's the core conflict, really. It's a philosophical divergence in how you even approach massive compute. Our whole mission here is to look at the architectures, the economics, and the, frankly, staggering strategic implications of this hardware war.
Right. So you can cut through the marketing noise and really understand who is set to power the next generation of intelligence.
Exactly.
So let's start with the reigning champion, the GPU, because its whole position as the engine of AI is, I think, one of history's greatest happy accidents.
It really is a total accident. When the first GPUs were being designed, the idea of them powering a neural network was pure science fiction. They were built for one thing.
Games.
Rendering polygons for titles like Quake or, Crisis. That's what they did.
And to really get the genius of the GPU, you have to contrast it with its older sibling, the CPU, the central processing unit. A CPU is latency optimized. It's smart, it's powerful, but it's serial. It wants to finish one really hard task fast before it moves on to the next one.
And the GPU is the inverse of that. It's all about throughput. It's a massive parallel machine built to handle thousands of simple simultaneous tasks.
Like painting a screen.
Right. It doesn't need to be a genius. It just needs to calculate the color of millions of pixels all at the same time.
And here's the connection that changed everything. The math used to calculate a pixel's color, which is basically a ton of matrix multiplications, is almost identical to the math you need to calculate the weight of a neuron in a neural network.
A perfect, totally unexpected fit. It was a gift to the AI field. And critically, NVIDIA didn't just sell the silicon, they built the software layer. They built CUDA.
Okay, so how big of a deal was CUDA at the time? Did people get it immediately?
Not broadly, no. Not at first, but what made it so crucial was that it let developers talk to these graphics cards using a general-purpose programming model. You didn't have to write graphics code anymore.
It unlocked it.
It completely unlocked it. It took this gaming hardware and opened it up for scientific computing, for deep learning. That software layer, built years before the AI boom, that's the foundation of NVIDIA's dominance.
So the GPU becomes this incredible Swiss Army knife. It can train LLMs, mine crypto, simulate weather. Its flexibility is its greatest strength.
But it has a hidden cost, an Achilles heel. Our sources call it silicon baggage.
Silicon baggage, what is that?
It's the architectural debt it owes to its gaming origins. The chip still has logic for graphics rasterization, for display engines, stuff that deep learning models just don't need. It's designed to do everything, which means it can't be perfectly efficient at just one thing.
And that one thing is matrix math.
Exactly.
And that structural inefficiency is precisely what pushed Google to build something completely different. It was a matter of pure necessity for them.
Absolutely. The story starts around 2015. Google engineers realized they were staring down what they called the computational cliff.
Okay, a cliff sounds bad. What were the numbers?
The numbers were terrifying. They estimated that if every Android user in the world used voice search for just 3 minutes a day, the demand would force Google to double its entire global data center footprint.
Double it, just for voice search.
Just for that. And doubling their footprint was, economically, logistically, it was impossible. They needed a quantum leap in efficiency.
So their solution was to just abandon the general purpose model altogether and build an ASIC. An application-specific integrated circuit.
Yes, and that word specific is everything. We have to stress this. A TPU is not a general-purpose computer. You can't install an OS on it. You definitely can't play Cyberpunk 2077 on it.
Right.
It is designed, down to the last transistor, to do one thing beautifully. Multiply matrices for neural networks. period.
So what's the architectural magic? How does it get that hyper efficiency over a GPU, which is already pretty efficient?
The magic is something called a systolic array inside its matrix multiply unit, the MXU. And to get why that's so cool, you have to understand the biggest bottleneck in traditional computing.
Which is the von Neumann bottleneck.
Exactly.
Give me the simple version. Why does it hurt performance so much?
Okay, in a traditional chip, the processor constantly has to run over to the memory, fetch some data, run back, do a calculation, and then run back to memory to write the result.
All that running back and forth.
It costs a ton of time and energy. It's like your desk is in one room and your filing cabinet is down the hall. You spend more time walking than working.
And the systolic array solves that by, what, putting the filing cabinet on your desk?
Kind of. Think of it like a rhythmic bucket brigade. Data flows into the chip once, and then it gets passed rhythmically from one little processing unit to the next. It performs the operations as it flows through without constantly having to go back to that main memory.
So it radically cuts down on the travel time.
Radically. And by stripping away all that other graphics hardware and just optimizing for that data flow, you basically crush the von Neumann bottleneck. And you get this massive, unprecedented performance per watt.
Which brings us right to the core philosophical debate here. Flexibility versus this hyper-specialization. Which one actually wins?
Well, the case for the GPU starts with a simple fact. AI research is messy. It's chaotic. You have new model architectures like Mamba or weird transformers popping up all the time. Researchers are constantly inventing custom activation functions or strange new layers.
And with a GPU, you can just do that. You write a custom CUDA kernel for your weird new idea, and you can run it on an NVIDIA chip like tomorrow. It's the king of R&D, the safe bet.
It's the Formula One car. It's built to handle any turn, any track you throw at it.
But the TPU?
The TPU is built for production economics. Once your model is stable, once it's deployed to 1 billion users, you stop caring so much about R&D flexibility.
Right, your focus shifts.
Your focus shifts entirely to two things: cost per token and joules per query. How much does it cost and how much energy does it burn?
So the TPU gives up some of that programmability for just raw, brutal throughput.
Yes. If your workload fits the standard math, the kind of operations in TensorFlow or JAX, the TPU just screams it's the dragster, designed to go incredibly fast in a straight line.
Okay, so let's break down where that plays out. Training versus inference.
Historically, training was the GPU's stronghold. You needed that flexibility for checkpointing, for debugging. The NVIDIA software stack was just so mature.
But that seems to be changing. The sources all point to this major shift, with Google training their flagship model, Gemini 3, entirely on TPUs.
That is the single most important data point in this whole conversation. It's a statement. It proves that these specialized accelerators are now mature enough to handle the biggest, most complex training jobs in the world.
So the gap isn't about capability anymore.
No. Now it's about ease of use. It's about the developer ecosystem around it.
And what about on the inference side, actually running the model for users?
Now that happens millions of times more often than training. And that is the TPU's home turf. This is where that architectural specialization really shines. Because for a hyperscaler like Meta or Google, a tiny efficiency gain, say 10% lower power use or 15% better throughput, that translates into hundreds of millions of dollars saved over a year.
Wow.
The TPU's architecture is just a better fit for serving stable models at global scale.
So the strategic choice becomes really clear. If you're a startup doing crazy R&D, you stick with GPUs. If you're a hyperscaler deploying a stable model, you have to lean towards TPUs for the cost savings.
Exactly. But we can't talk about competing with NVIDIA without talking about the real lock-in, the software, the infamous CUDA Moat.
That moat is legendary. For 15 years, every library, every tutorial, every framework was optimized for CUDA first. It just locked you into NVIDIA hardware.
And the sources are now suggesting that Moat is drying up, or at least people are building bridges over it. The rise of high-level frameworks like PyTorch 2.0 and JAX is the great equalizer.
Because they're becoming compiler-centric. What does that mean for the average person?
It means we're moving out of that old era of hand-coding CUDA, where you're down in the weeds optimizing instructions. Now, a developer writes high-level code in Python, and the framework's compiler.
Like XLA for Google.
Exactly, like XLA. It intelligently compiles that code down to the most efficient machine instructions for whatever hardware is underneath. Whether it's a GPU or a TPU matters less and less because the compiler handles the friction.
So the technical lock-in is getting weaker.
Precisely. The lock-in is becoming less technical and more strategic.
Which brings us back to that Gemini 3 announcement. It was a statement of independence. It proved their whole vertical stack. The chip, the interconnects, the JAX software, it all worked at scale.
It was a massive signal to the market, a validation that the TPU is a battle-tested alternative. And this gets us to the really interesting catch in all of this.
The catch.
The catch. The big one is about accessibility and ownership.
Right. You can't theoretically walk into a store and buy an NVIDIA GPU. You can put it in your own servers. You own it.
But you cannot buy a TPU chip. You just can't. Google only sells the time on those chips, and only through Google Cloud Platform.
And that creates a whole different kind of vendor lock-in. With NVIDIA, you're locked into the architecture, but you can move the physical chip from, say, AWS to Azure. With TPUs, you are married to Google Cloud.
That's the critical boardroom decision. For a company like Meta, yeah, using Google's TPUs might be way faster and cheaper, but it means you are relying on a direct competitor for your most critical infrastructure. It is a huge strategic gamble.
So let's synthesize this. Let's build a concrete decision framework for, say, 2025. What are the clear choice points?
The NVIDIA GPU is still the default standard. You choose the GPU if you need maximum flexibility for R&D, if you're dealing with diverse code bases, or if you absolutely need on-premise deployment. The software is mature, it's dominant, it's everywhere.
And the TPU path?
The TPU is the choice for ruthless efficiency. It's for large-scale, stable training and inference where that cost per query is the most important metric. The software, JAX and XLA, is growing fast, but the hard constraint is it is Google Cloud only.
The choice really boils down to portability and freedom versus pure performance and cost.
Yeah.
If you're debugging some wild new architecture, you need a GPU. If you're serving a model to 1 billion people, the TPU's economics are just incredibly compelling.
And that means the era of the monolithic AI hardware market is over. This war isn't zero-sum. It's a diversification of the supply chain, which, at the end of the day, is great news.
NVIDIA is still the standard for innovation because that ecosystem is so deep.
Yeah.
But like you said, the CUDA Moat isn't a prison wall anymore.
It's becoming just a fence you can step over with the right compiler.
And Google proved that vertical integration, designing the chip, the data center, the software, and the model, all together yields results that off-the-shelf hardware just struggles to match.
Yeah.
So for you, the developer, this competition is just fantastic. It drives prices down, innovation up. The choice between a TPU and a GPU is becoming, as one source put it, just an implementation detail defined by a compiler flag.
And that's the thought we want to leave you with. As these compilers get smarter and abstract all the hardware away, these massive performance advantages, like the TPU's efficiency, they're going to outweigh portability concerns more and more often.
So the question to mull over is,
how long before that cost per query advantage gets so big that it convinces everyone, even the smaller players, that it's worth marrying themselves to the one cloud provider that has the most efficient custom silicon?